Welcome everybody to today's webinar. This is Ben Salisbury with GNOME. I will be moderating the presentation. Thank you all for joining us. Our speaker today is Dr. Michael McManus. He's GNOME's Senior Vice President of Operations. He'll be speaking about hardware requirements and considerations for the analysis of next-generation sequencing data. To make it a bit more concrete, he'll explain how GNOME has addressed these issues in the design of hardware to accompany the Gnosis NGS analysis and interpretation system. Michael has a long history in computational hardware. He worked at Fujitsu, where he was involved in supercomputing hardware design. He's also spent several years in computational chemistry at Kodak and Cambridge Soft. If you have any questions during the webinar, you can type them into the questions box in the GoToWebinar control panel. Before I hand the presentation over to Michael, I wanted to do a quick poll of who's in the audience today, what your experience and interests are with hardware. Please take a minute to choose the option that best describes you. It should show up on your screen now. Okay, another couple seconds here and I'll close this down. Oh, I do see more tallies coming in though. Okay, great. I'm going to close this and let's take a look at the results. Okay, so it appears that many of you already have hardware that you're using for NGS analysis. Of course, those needs change over time. A lot of you are considering or are just here to learn. So that's terrific. Thanks for volunteering that. I'm going to hide this and we will get back to our presentation. So before I hand over to Michael, I just want to remind you that you do have the opportunity to drop questions in at any time during the presentation, and we'll have a Q&A session at the end. Welcome, Michael.
Thank you, Ben. Hello, everyone. Thank you for taking time out of your busy day to listen to the next hour's worth of hardware details. As you can see, we have 4 questions that we intend to answer. And of course, there are many things that you need to think about when it comes to NGS informatics and hardware. As you know, there are choices out there that go from the cloud to hardware that you have already in-house or to hardware you might acquire. There's also the type of hardware you might want to use, and there's specifically the specifications that you may need to consider. And then you get through all this, and you have many vendors that you could potentially choose from, and you have to figure out, how do I even know which vendor to use? How do I look at one vendor versus another? So I will go through these questions, and we'll see where that takes us, and we'll take questions at the end. Before I jump to the first question, though, I'd like to just remind everyone about what GNOME's NGS informatics workflow looks like, just so you can get a sense of a workflow, one that we use. And we have this workflow as shown on the screen here, which starts from aligning and calling and goes all the way to reporting. And as you could imagine, the left-hand 3 items, align, call, and annotate, are what we call upstream. And then there's downstream for filter, classifying, and reporting. The upstream piece is really the realm of bioinformaticians and technologists, and the downstream piece is really in the area of expertise for geneticists and clinicians and, of course, genetic counselors. In addition, obviously we need to provide fast and flexible bioinformatics. We need to really have a good set of reference data that's comprehensive for the annotation stage, and there need to be tools that provide filtering and other prioritization, things related to the disease that help you do the interpretation. So this is what we have as our informatics pipeline. So I'm going to return now to answering the questions, and then we'll come back again to some more GNOME-specific details in a little bit. So this is the first question. Why internal versus using the cloud? Now, GNOME's customers have, believe it or not, expressed a very strong preference for internally installed solutions versus using the cloud. Seems contrary to what's out there in terms of all the cloud solutions that people see. Similarly, we were surprised at first with this kind of feedback, but the reasons they gave us are quite clear and understandable. Obviously, at the top of their list is security. These customers are very nervous about the content of the data that would be on the system. For example, a patient name perhaps, their DNA, their variants, various associations that we may have identified. And so these things are important for them to keep in-house behind their firewall. And so this is a major, the primary reason why they insist on an internal solution. But another pretty closely important reason is software version control. Many of these places are required to have complete control over the software that they use to process genomic data. And they don't really have a lot of choice in the sense of not complying. They have to comply. And in a cloud-based solution, they find often is the case that the software updates change without their knowledge, and it leaves them in a position where they're somewhat uncertain as to what results may have changed from one software version to another. So they prefer to have complete control over the software version and decide when they make that actual software shift. Another reason why they really like something internal. Of course, another important reason is file transfer time for them. Some of these files that come off of the sequencer can be from low number of gigabytes to hundreds of gigabytes. And to transfer a file of that size over the internet, of course, is doable, but it's, if you have an internet connection that's not exactly built for transferring large files, as many of these facilities, this is the case at many of these facilities, and then you layer on top of that the concept that they might be doing volume, not just one at a time, they may be doing 10 or 20, depending on the volume of the lab, and that combination of large files, and many of them, with an internet connection that perhaps isn't robust enough, makes it very difficult for them to rationalize how they could live in a cloud-based deployment at this point in time. So those are the three reasons that we often hear from our customers and why we are so, not quite singularly, but largely focused on an internally installed solution. So with that, I will just switch to question 2. So now we're asking, what kind of hardware, what sort of hardware should we consider? And of course, this question depends on the answer to a number of questions. For example, what is it you're doing? What kind of software are you going to be running? Are you going to be aligning and calling? Are you going to be reading VCF files? Are you going to be doing whole genomes, full exomes, or just panels? What kind of sequencer do you have? All of these questions factor in. There's additional questions too on the software. How many users will be accessing your system? How many samples a month, for example? And so these all in total add up to a series of needed answers that you have to get before you can really start to define the hardware that you need. Of course, here at GNOME, we have thought about this a lot, and there are 5 elements that we feel are really important for NGS informatics, and that's shown on the next slide. These 5 elements are really, I think they're relatively straightforward at a high level, but there are a lot of details that may not be so obvious. First of all, you have compute, you have database, you have storage, you have networks, and you have software. So let's go back to compute for a second. The compute, we believe strongly that others should be using a multi-node approach when they do computation. There are so many tasks to be done in NGS informatics that if you have a multiple node solution, you can actually do a lot more in parallel than you would otherwise be able to do. And along with these multiple nodes, grid computing, a way to distribute and control your jobs by dispersing them over these multiple nodes is a very useful tool. Grid computing has been used for over 30 years, but it hasn't always been called grid computing. But in fact, the distribution of jobs over multiple CPUs and multiple nodes has been around a long time. Just more recently, it had the name grid computing. Databases are important because you are running samples, and there's a lot of metadata associated with samples that is important to record, and there are results from running these samples that are equally important to record and to associate with a particular sample. So, having a database to keep track of things that are processed through a system, an informatics system, is pretty important because it allows you to look back over time and see what's been done and to perhaps learn what maybe you should be doing different in the future. Of course, next is storage, and this is a big part of any solution. How do you store all the data that you're actually producing? And how do you do it in a way that makes it robust and fast enough? So you have a few issues there. Now, GNOME's a big believer in a shared file system, and simply a shared file system is just a file system that allows a number of servers to have access, but the shared file system arbitrates who has access at any given time. And it's important because in a multi-node system, you could have a situation where you're writing your data and results and temp files and all the things that happen with your computation to the disks that are local to the nodes, and then you have to rectify how you clean up all that data, how you get it all together and integrate it. Whereas with a shared file system, everything, including temp files, is written to the shared file system, so it's all in one location. Makes life a lot easier when you consider things from this perspective. So I have actually more information on the shared file system. I'll talk to you. I have a couple slides ahead, so we'll come back to this. The next thing is networks. So you have a multi-node system. How do they communicate? Well, you need a communication network, and you also need a network for storage traffic because you don't want these two colliding. So you'd like to separate the traffic for writing files back and forth to the shared file system from the traffic that's basically communication from one node to another. And of course, you have this, your system, you want to get files on and off of it, so you need to have some kind of provision for network access to allow file upload and file download. And then finally, you have software. And it starts with your operating system. What OS are you going to run on your hardware? What does your software require for an operating system? Do you want to use virtualization? And actually, GNOME has, it does use some virtualization, which I'll explain later. There are also many open source tools, and a lot of those tools can save you time. If they're well understood and documented, you can actually use those open source tools instead of writing your own software. And that's just an important consideration when you're thinking about the mix of software that you're running on the hardware that you're trying to define. And finally, GNOME is a big believer in using web technology as a way to interact with these systems. So it's nice if you can have a web server that actually serves up web pages so that you can interact with the system from your desktop. And that really is those are really the 5 elements that we feel strongly are important for NGS Informatics. So I want to give you just an example. So I talked about multiple nodes. So this is just a quick overview of, I don't expect you to read all this or understand it, but this is a lot of stuff that's going on the Gnosis system. But what we've done is all of these tasks don't run on one node. For example, we see that some of it runs on an application node. Some of it runs on grid nodes, there's many of them potentially on your system. And then you have also a database node. And in addition to that, you have the shared file system that runs underneath the file system manager. And then within the shared file system, you have data nodes. And so this multi-node system that we're talking about, or approach, is something that distributes a lot of the tasks across multiple nodes. And this is just one example I wanted to share with you. So now I want to talk a bit about a shared file system. And a lot of text here, but basically there are really 3 points, and the details are underneath. Shared file system, as I said earlier, everything's stored in one place, not on separate nodes. You need something that's failure tolerant, and you need performance. So at a high level, those are the 3 things that you need. Of course, within failure tolerance, I mean, there's things like RAID 6, which we're strong believers in. You want to be able to tolerate drive failures on your system. You'd like to have some sort of spare drive in case of a drive failure. And you'd like to have a decent array reliability rate, something above 90%. Those are important considerations when you're using a system that could be mission critical. Of course, you know, failure tolerance is really critical, but also it has to be fast enough. And so you want a file system that actually supports striping, that goes across a series of drives. This is something that also is good for performance. And a system like that can also get faster as you add more disks. This is another important piece. As your storage requirements grow, you don't want your storage to get slower, you want it to get faster. And typically, you want a decent input-output for I/O rate. And we'd love to see something at least around 1 gigabyte per second. And this is all achievable with certain shared file systems. Again, I'll give you more details on GNOME's solution to this in a few slides, but just wanted to set this up as one of our requirements or recommendations for NGS Informatics. So with that, we'll proceed on to question 3, which really is what hardware specifications are needed. So are we going to do aligning and calling, or are you going to do interpretation? So these are important considerations and help further refine the specifications and decisions that you might need to make. So let's just start with aligning and calling. You know, as we know, it starts with a FASTQ file, produces a BAM. BAM is taken by the calling software to produce a VCF. This process takes a large amount of RAM and disk space and cores. I mean, typically you're thinking about, you know, a minimum of 8 CPU cores and 64 gigs of RAM to do some of these tasks, depending on the aligning and calling software that you're using. If, you know, so that's something to consider. Now, if you want to talk about interpretation, that typically starts with a VCF file. These files are smaller. They're, you know, to the hundreds of megabytes to a few gigabytes, versus FASTQ files, which can be hundreds of gigabytes. Now, this annotation process that GNOME uses, and the interpretation process also benefit from a lot of RAM, disk, and CPU, but to a lesser extent. So even outside of GNOME system, anyone who's doing this interpretation process and annotation process, you know, would also benefit from these amounts of RAM, lesser than for aligning and calling, but still not inconsequential. A normal VCF file can pre-process with about 2 CPU cores and about 8 gigabytes of RAM. So, you know, most people on their laptops might have 4 or 8 gigabytes of RAM alone, and if you're doing multiple files, either aligning and calling or interpreting them through a VCF, you know, you can imagine that you have to have a fair bit of additive amount of RAM so you can run these things in parallel. So just something to keep in mind. So what I'd like to do now is, with this information, show you how we chose to solve the problem, because I think it'll give you a concrete example of decisions we made as we came to design the Gnosis. So just, you probably know this, but I'll say it again. It's an end-to-end reads-to-report system. You can read these bullet points, but it allows for people like bioinformaticians and technologists, as well as geneticists, genetic counselors, and others to use the system. It can be used translationally in a translational lab or in a clinical lab, and there are several configurations that are possible in the design of this system. So the larger system that we start with is the align and call, for aligning and calling, is the K100 system. And this is really designed for large numbers of whole genomes and exomes. And to give you a sense of scale, there's a person standing next to one of the Gnosis units. And so it's about a half-height rack. It's a 24U rack, and that's how it's shipped out. There's room for expanded storage as well. As your storage needs grow, we can add additional storage. And then there's the Gnosis K25. And this K25 model is really the one set up for interpretation. This is the one geared more at VCF files, processing panels, but to some extent smaller numbers of genomes and exomes. So this is a 2U system and designed to go inside the server room on a rack, but it's a fairly capable system. And just to talk about some of the specs, so hopefully these are visible. If you look on the left, the box labeled K100 specs, you can see this system has actually 8 different servers inside of it, 8 nodes. It has a total of 98 cores, physical cores, and about almost 700 gigabytes of RAM, and about 80 terabytes of onboard storage. It also comes with, from a networking point of view, a 1 gig network, an InfiniBand switch and network, and a 10 gigabit Ethernet card. So what we're doing from a network point of view is the 1 gigabit network is the communications network, the InfiniBand is the storage network, and the 10 gigabit card is what you use for file uploading and file downloading. But you'll see you have 4 compute nodes, 1 database node, and some storage nodes. Similar to the image I showed earlier in this presentation. The K25 model actually, as you will note, has 1 node, pardon me, and 2 CPUs and 16 cores, but about 256 gigabytes of RAM. And it uses 10 gig Ethernet and 1 gig Ethernet, but not InfiniBand. So these are designed for different purposes. But if you look at the throughput for the K100, you'll see it does about 60 whole genomes a month via line and call, and almost 1,500 VCFs a month just for the annotation process. Whereas the K25 is a bit slower on the align and call. It does about 12 whole genomes a month and about 360 annotations a month. Similarly, it can do a fair number of exomes, 54, and K100 can do about 270. So these numbers are designed to deal with different lab volumes. Of course, the K100 model is designed to be expandable. So if 60 genomes a month is not enough for you, we have a very scalable solution, so we can add more grid nodes very easily and get your monthly genome capacity to be as high as you need it to. We can also scale the storage to very large amounts. So, speaking of storage, what I'd like to do is talk about the shared file system that we use first on the Gnosis 100, or the K100, and then secondly on the K25. So, it's a little bit of a busy slide, but let me start here with the configurations. So, there are 2 configurations that we ship for the K100. One is with 60 terabytes of onboard storage, and one is with 180. Now, there's lots of jargon here. An SSU is a scalable storage unit, and a picture of the 60 terabyte unit is here on the upper right. This is a system that has 80 terabytes raw and 60 terabytes usable for the actual shared file system. And as you'll see, this diagram is trying to show you that there are 21 drives inside of this enclosure, as listed down here, 24 terabyte drives and 1 hot spare. The hot spare is this red one off to the right. And the drives that are marked out in X are the parity drives. These are the drives that are set up as part of RAID 6. So this system has it can survive basically the failure of 2 simultaneous drives. But if one goes, the hot spare picks it up and fills in, and then you can actually replace the failed drive later. I/O rates for these, the maximum I/O, though these are the theoretical max, are about 2.5 gigabytes a second for the 60 terabyte array, and about 7 gigabytes a second for this larger array, which is this 180 terabyte config. So the difference between the upper one and the lower one is that we're adding things called expansion storage units, which are very similar in structure. Again, 21 drives each, 20 for storage, of which you sacrifice 2 in each of these arrays, and still a hot spare. So in this config, you end up with 3 hot spares. So that's the larger solution. Of course, I mentioned InfiniBand here because the way this is a balance issue that I mentioned, the balance of the 5 elements. So if you have a system that's capable of delivering an I/O rate of 2.5 gigabytes a second, it would be silly to have a network on your system that can't actually handle that bandwidth. So the choice of InfiniBand was really to allow this. So we have an InfiniBand system that's capable of 7 gigabytes a second, which it was chosen to be somewhat matching to the maximum I/O rate of the larger configuration. Hopefully that's clear. And of course, this array has a reliability rating of about just under 97%, which is really good. So that's the shared file system for the K100. Now, of course, the K25 has a shared file system, but it's not Lustre. It's actually a RAID 6 array, and it's much simpler, but it's also designed for lighter duty. Basically, for the K25, we have just 8 drives of 4 terabytes, so that's 32 terabytes raw. And in RAID 6, 2 become parity drives, and you end up with 6 for storage, so 24 terabytes usable. And this has a maximum I/O rate of just under a gigabyte per second, and in reality it'll be less, but that's still a pretty good I/O rate. And this array reliability is slightly less, still above 90% that we like to see, but it's a couple percentage points less than the Lustre array. So this is our shared file system. So this is the concept that the balance between the compute and how fast you can compute the data, how fast you can move it on and off the shared file system, and how fast your database can keep up, how fast your network is. These all have to be tuned so that you get the maximum performance from your solution. So with that, I will proceed to the last question, which is, how do we compare, or how do I compare systems that are apples to apples? And this gets back to the question of there are many choices. And so for a lot of people, all hardware sounds similar. And again, I keep emphasizing the 5 elements. All hardware is kind of similar. I mean, yes, there are different vendors, and the Gnosis, is built with some hardware, but the components we use are available from multiple vendors. But for us, the value that we brought was really the combination of the various elements, as I've explained, and the price performance that we offer. And you have to make some decisions about, there are more expensive solutions, there are less expensive solutions from a hardware point of view, but it's that combination of performance and price that you have to optimize. It's kind of like a max-min problem for those calculus fans out there. So what I'd like to do is just give you a quick overview of how our system's constructed. This is the K100. And this blank outline that you see is actually the outline of a 24 rack unit rack, a 24U rack. So basically what we do is we start with this high performance compute server, which is a 4-node system, has 8 CPUs in it, and today it has half a terabyte of RAM, but can be upgraded to 2 terabytes of RAM for this one node. And there are 3 grid nodes in there for doing the computation, and 1 application node for the web server and serving up the web-based user interface. This is the unit of scale that we would use to add more capability for adding more genomes. So of course, along with this, we would have to consider other elements like network and storage. So we have a database server as well. This keeps track of everything. We happen to use Postgres. Go into that in a little bit more. And this is what keeps track of the transactions and all the processes that happen. And then you have to store everything. And so here we have the storage unit that we're using, which is the 60 terabyte, by default, 60 terabyte array. And it comes with a storage management unit, which is for storing metadata for all the files. Now, this is a very high availability system. It has, as I mentioned, redundancy. It has two metadata servers built in, so one for failover. It actually has the hot spare drive built in, and so this is a very it's designed to be very available, and as is the case you would expect in a high demand NGS informatics situation. It's also expandable, so we can add extra storage units as your storage needs grow. Even within this one rack, of course, if you outgrow the rack, bigger racks are around, not a problem. And then there's the network. As I mentioned, how do these all intercommunicate? And well, you have a gigabit Ethernet switch for just regular network traffic, and then you add an InfiniBand switch. The QDR here, I'll explain on a following slide, but the InfiniBand switch manages the storage traffic, and so all the machines or nodes are interconnected by two different network connections in this drawing. And of course, depending on where you put this, you need backup power. So you can put a UPS in there, and that UPS serves two purposes. One is if the power goes out, it keeps the system running long enough to shut it down, but it also conditions the power, so if there's spikes or dips in your power, you can filter those out with the UPS, which is really good for the longevity of your hardware. So continuing on, just to try to summarize the elements that are different here, there's a three-column image here. We have a K100 column and a K25 column. Some of these are in both columns, meaning they're in common. But let me just review. So the K100 has 4 physical nodes from a compute point of view. 3 are specifically for grid, and 1 is for the application node. And the K25 actually has 1 physical node, but 3 virtualized nodes. We're using a virtualization software. 2 of those are compute, and 1 is application. So structurally, or logically, they're similar. It's just in one case it's physical hardware, and in the other case it's virtualized nodes. Both use Postgres. In the K100 case, it's physical, and in the K25, it's a virtual node. As I mentioned, the K100 uses the Lustre shared file system, and the K25 uses a RAID 6 disk array. The storage network, this QDR, FDR, InfiniBand, QDR stands for Quad Data Rate. It's basically 40 gigabits or 5 gigabytes a second of I/O rate or I/O bandwidth. And FDR is, these abbreviations are strange, but 14 data rate, and really is 7 gigabytes a second. So the technology we use for the InfiniBand is hot switchable from one bandwidth to the next. So as your needs grow, you can instantly switch your InfiniBand capacity. Over here on the K25, we're using SCSI attached serial, so SAS drives, for the RAID 6 array. Both have gigabit Ethernet and 10 gigabit Ethernet for file uploading. Both actually have a Tomcat web server running on them, and on the desktop side, you would run Java and Chrome as your client for accessing the system. We're using Red Hat's open source CentOS versions 6.3 and higher, and a lot of open source tools. Of course, the K25 is using VMware as its virtualization technology. And these systems are very similar in a lot of ways, logically, but physically are somewhat different. So that takes me basically to our conclusion, which I think should be rather self-explanatory. The cloud has great potential in my mind. I mean, I actually used to work at a cloud-based company before GNOME. But for genomics needs in the clinic, we are seeing a very specific focus on in-house solutions. And of course, when you're deciding on your hardware, what to buy, I mean, there's so many decisions that you need to think about. And not only about the different files that you're using, but the number of users, the different software that you're using, the number of samples. So there are many things that you need to keep in mind. And even if you're buying your own hardware as opposed to our solution, you have to think this through before you make these purchases. And again, comparing hardware from one vendor to the other is not necessarily simple, but as long as you focus on your end goal and what it is you need and how your design meets that need, usually in that process, the vendor of choice will fall out and you'll know what you need to do. So with that, I think I will transfer it back to Ben and let him take it from here. Thank you all for your attention.
Thank you, Michael. And if you advance to the next slide, I'd like to let you know that there is a recording available of this, or will be available of this webinar that we just attended for you and your colleagues' reference. I'd also, as you type your questions into the GoToWebinar control panel, also like to let you know that registration is open already for our next two webinars. On October 30th, Dr. James Crawford from Hofstra North Shore LIJ School of Medicine will be speaking about the business of genomic testing. And then on November 13th, we'll have Dr. David Goldstein from Duke University presenting on precision medicine in neurological disease. And Jessica has just dropped links to those registration pages in the GoToWebinar chat pane. So, Michael, we do have some questions here. This hardware that you described, these seem to be systems that are designed to go in a server room. Can they also be set up in a lab?
Well, yeah, it's interesting that that's an interesting question. Originally, when we were designing this system, we had thought that it would be great to have it in the lab. But of course, these systems produce a lot of heat and have a lot of spinning hard drives, and so they tend to make noise and require a fair bit of space around them if they're not in a server room environment. So we advise that they go into server rooms as opposed to rather expensive lab floor space, where you often, if you leave enough room around the system for the cooling, you end up taking up a fairly large rectangle of lab space, and people don't like the noise. So we recommend a server room environment for these because it's temperature controlled and access is controlled, which is often a concern for people about security. If there's genomic data or genetic data on these systems, most people want them locked up so that they know who's accessing the system when.
Okay. So here's a related question. So if it's going into a server room, does that mean I'm relying on my IT department? How much effort is involved in setting up one of these systems and maintaining them from the IT perspective?
These systems typically, let's talk about the K100 for a second. The K100 is, for us, if we're talking about our system, is shipped fully assembled in a large crate, ready to go. So if there's room in a server room for it, then we ship it assembled in a rack all together, and it gets plugged in. The IT requirements we typically deal with in advance before we ship the system. Like if we need IP addresses and other kinds of access, we do all that in advance through a site survey process that we use with our customers. Certainly, if you're buying hardware from a vendor in general to add on your own for your own solution, the IT department would, of course, be involved, but they would probably go through a similar process of trying to make sure that the end user, the scientists or clinicians who are specifying what they need are getting what they need, and that all these details are handled. But you do need some IT involvement, but once the system's up and running, that IT involvement should be less than you would expect.
Okay, so this is another kind of location question. So do sequencers directly hook up with the hardware? How does that work?
Well, they can. It depends on what comes on the sequencer. If a sequencer is equipped, for example, with some hardware underneath, some of these sequencers do the align and call already and produce a VCF file, in which case you just need to find an easy way to get the VCF file from the sequencing computer to your hardware solution. In our case, we provide InfiniBand switch that has extra ports in case someone uses InfiniBand, but we also provide a 10 gigabit Ethernet card in case someone prefers 10 gig Ethernet. Now, the InfiniBand solution that GNOME provides is 4 times the speed of 10 gigabit Ethernet, but whatever works, there are extra ports so that you can plug the computer that's affiliated with the sequencer into, in our case, into the K100 model or K25 model and transfer the files directly over. It's not a problem. Obviously, if it's your own hardware, you can make similar design decisions and make sure you have the right kind of fast network to go between your hardware choice and the sequencer.
Okay, and I guess this ties into that as well. So, is there what effect does this have in terms of uploading files to local hardware through those kinds of connections versus up to the cloud? What kind of speed difference is there? How does that relate to the kind of volumes that the labs run?
Yeah, that's a good question. I mean, if you have a 400 gigabyte file and you are for a FASTQ file coming off a sequencer, and you're trying to upload that over your internet connection, I mean, it's enormously difficult if you don't have a reasonably fast internet connection. So if you go back to the old days with a T1, I mean, it would take you almost a month to transfer a file like that, depending on how much latency you had and how much your connection's being used. But most people have way more than a T1 now. If you look at just the 100 megabit Ethernet connection, I mean, it can take 9+ hours to transfer a file that size on an internal network. So it's really difficult. That's why our solution was to provide InfiniBand, because on an InfiniBand network, you can transfer a file in under a minute that size. So one of the things that's really important is that to our customers is this internal connection allows you to make some of these decisions much more easily. You can decide to put an InfiniBand card in your sequencing hardware and get this very fast 5 to 7 gigabyte a second transfer rate. But if you're trying to do this over the internet, unless you have extraordinarily fast internet connections, which most of us don't, you do have to wait. And then if you're doing this dozens at a time, it becomes a very difficult problem to reliably upload lots and lots of files.
Okay, great. Well, thank you again, Michael, and thank you everybody for coming. Hope to see you next time.
Thank you.